Okay, data assimilation. What's data assimilation? So, in so many systems, what we do, trying to figure this out, you will have a model, and often what we do to represent models, to create models, is we break the system up into grid boxes. And we'll have points or a grid box that will associate average values. In the atmosphere, it might be U, V, the components of the wind, the temperature, the relative humidity, cloud liquid water, cloud frozen water, aerosols. You can go on and on. If you had pollutants in there, you'd have pollutants as well. Yeah. If we want to make a forecast, what we need are initial conditions. But anyway, normally whenever you do this, you have some prior estimate of the state. So if you went to if somehow you had a great model of a system and you'd never had observations of it, I imagine that would almost never happen. You kind of need observations to create good models, but you could try and do it from first principles. You might create a climatology of that system, yeah? And so before you take any observations, maybe all you'd know was climatology. And by climatology, I do not mean the climatological mean. By climatology, I mean the probability density function of all the states that can happen on that planet. Yeah? So like today, we have a realization of our climate. Yeah, if you looked at the map today. And so there's a distribution of all those. That's what I mean when I say climate. And you could randomly sample that climate to create those historical states, if you like, to create an ensemble. So this X letter there, when I write that and it's bold, that is a very long vector. And it lists every single variable in your model. Yeah? So in a typical atmospheric model, that'll be 10 to the 7 variables, depending on the resolution, 10 to the 6 to 10 to the 8 variables. And we won't just have one realization of that, we'll have K of them. And typically in atmospheric and oceanic applications, K will be somewhere between like 15 and 250. Yeah? So that's prior information. Yeah, that you've got these states, you've got some sort of prior information. And then what we have is a whole bunch of imperfect observations. Aircraft are taking observations as they fly around and they share them with everybody. The main reason they take observations is to monitor the performance of their engines, because their engines depend on the engine performance depends on the weather conditions, but they share it globally because they need weather forecasts really badly. What else have we got here? We've got a weather balloon here. So you can fill a balloon with helium and tie to the bottom of it a sensor that's going to measure temperature and humidity. You can also track the balloon to see how the balloon's getting blown around. And from that, you can get the wind, not just the speed, also the direction, at least the horizontal components of the wind. You can have an ocean buoy like this, which is measuring the SST. If you've got an anemometer on it, you can measure the wind and the temperature above it. Here's a radar. So radars, well, they have different types. You can design them to measure like cloud particles, or you can design them to measure rainfall. That's very close. What's that one? I think that's another anemometer. And then, of course, we have loads of observations in space. Yeah, there's all these satellites going around the globe. But of course, you know, our models, the variables they need are things like the zonal, horizontal, and vertical components of the wind, the temperature, the relative humidity. You can't detect that from space. The only thing you detect from space are photons. Yeah? That's it. And so there's this huge challenge of turning these measurements of photons we make from space, where we get global coverage, into the things that the model needs to be initialized, which is things like UVT. Okay, so what data assimilation does is it combines information from this prior ensemble forecast with these imperfect observations. And then, obviously, when you do that, you take into account the uncertainty. Somewhere out there, there's a true state, yeah? We believe that. There's this one true state. And this isn't it, and neither is this, but they both have some statistical relationship to the actual truth, and so you can combine those two bits of information and come up with what we call an ensemble of posterior analyses, so, after the fact. So prior ensemble forecast, posterior analyses, an ensemble of analyses. So the ensemble of analyses we get here are much better informed, because they're informed by these observations, than what we had here. In the atmosphere for global weather forecasts, most centres perform this operation every 6 hours. So every 6 hours they take a prior ensemble forecast, they combine that with observations, and they produce an ensemble of analyses. And then from that ensemble of analyses, they make an ensemble forecast, which creates a new ensemble forecast. So this new ensemble forecast is informed by the observations we took here. And if the first time we just started off with climatology, this sort of second ensemble forecast we got would have been much better than the first one. If we have a very, very good model, information from these observations can be preserved by the model as you make the forecast through time. And so the next time, 6 hours, we went forward 6 hours, we produced this ensemble forecast, then we're going to combine that with new observations, like observations that were taken in the last 6 hours that the system has never seen before. And so we add those in. So now, once we've done that, now we've got the observations from the first time and the second time. It's like we just doubled the amount of observational information that went in there. And that observational information between the two times, say this was 0 UTC, and then the second time it was 6 UTC, how much of that information was preserved depends a lot on the quality of this model. So I hope already you can see that data assimilation and model development are tied at the hip. If you can make the model better, it helps data assimilation, because the model will better hold on to the information from observations taken at one time to when you get to the next time. And similarly, if you improve data assimilation, one of the things that data assimilation does, you're coming up with these state estimates. If you can throw gazillions of observations at this state estimate, you can get a really good state estimate. And then, when you make this forecast, you get to see how this forecast is wrong. And often you'll see it's systematically wrong. It's systematically wrong with clouds. It's systematically wrong with the position of jet streams. There's all these things that are wrong with it, And data assimilation is this beautiful way of combining every single observation that you assimilate, and normally this is a number like 10 million to 10 million observations, to estimate a state. And then when you compare your forecast with that analysis, it exposes model errors. And so they really work together, these two things. So so I want you to have in your mind that there's in practice, there's always a data assimilation cycle. So for most centres at the global scale, every 6 hours, they combine information from a forecast with information from observations. So there's one at 0 Greenwich Mean Time, 6 Greenwich Mean Time, 12 Greenwich Mean Time, 18 Greenwich Mean Time, 12 Greenwich Mean Time. But different centres do it differently. The European Centre for Medium Range Weather Forecasting does it every 12 hours. They're really aiming for accuracy in like 5 to 12 days. Most of the other centres are probably more focused on 1 to 5 days. You guys, for the seasonal forecast, what is it, every like 4 days you do it, or? I can't. Right, but so seasonal forecasting, it's not, at the moment, it's not even every day. It's like every 4 days. And people doing ocean data assimilation. So the thing I'm describing here, you can do it for the ocean as well. But the ocean changes pretty slowly. And so often people doing ocean data assimilation, their data assimilation window will be 10 days. Yeah?
Must be daily for the seasonal, because
sorry?
we're actually doing 33 members every day.
Right, yeah. You guys are doing the daily. But there are oceanographers who will have these 10-day windows. And you know, we atmospheric people look at that and go, oh my God, that's a long time. And then also, like if you, so I think if you're doing, trying to do very high resolution forecasting, say for a city, and say you're assimilating radar observations of convection, often this data assimilation cycle, it might just be every hour you do an update, even down to 15 minutes. I don't think anyone's doing 15 minutes. I think operationally at the moment, it's the shortest people do is an hour. But they kind of like to do shorter time. So whatever data assimilation system is, there's some sort of cycle going on like that. Okay, so to what extent does data assimilation contribute to the accuracy of weather forecasts? That's a question we could ask. So here's a slide from the Met Office. And as Matt Wheeler just mentioned, Australia uses the Met Office system. And the Met Office has a skill score, which is based on the performance of their global model and their regional model. Sort of summarizes everything. It's kind of for a UK user rather than an Australian user. But what you see, so this is from 2011 to 2017. Oh, sorry, this is just the global model. I think that's right. So this is probably just pertaining to the global model. But anyway, the 5 biggest impacts were due to improvements in initial conditions or data assimilation. So we can just run through those. This is the biggest one, this one here, plus 2.44. I mentioned before how, like, to do data assimilation, you have to characterize the uncertainty in the forecast and the uncertainty in the observation. Yeah, so this change they made here was just improving their description of the uncertainty in the forecast. That was it. Yeah? It wasn't assimilating any new observation type. It wasn't some fancy new instrument they put into space. It was just better characterizing the errors in the forecast model. That's it, yeah? So the theory and the way the data assimilation scheme is designed is hugely important now. So the ECMWF was set up to do 10-day forecasts. Yeah, that was their initial mission. They're going beyond that now, but that was their initial mission. And originally they thought, we'll do one deterministic forecast out to 10 days. So just to give you an idea of how much importance the ECMWF puts on data assimilation, currently I think that data assimilation step takes an hour. Yeah, so assimilating all this data and doing everything they can to, like, get the data in there as well as they put it, that's an hour's worth of computation on this enormous supercomputer. The time it takes to do their high-resolution forecast, that single forecast, that was the prime thing they were going to do, I think that's like a minute. Yeah? So I think it's seasonal forecasting, it's probably 50-50. I don't know, but it's sort of that's the way the field's kind of gone, just enormous amounts of effort into this part in terms of the computational expense. All the other ones were less good. So this is, that was the first photobar that was improving it. This is getting some dust in. This was including improving the variational bias correction. That's actually a big one. That's really close to that. So this was the vast majority of our observations today are satellite observations. And it's this problem of turning photons into things like U, V, and T. I don't really want to push this in too much, but where do we have? See this end game? That was a change in the dynamical core of the model. Yeah? So they actually changed the way the numerical integration was going. And it's actually a degradation. But anyway, yes?
How does the KPI impact computer?
Sorry?
How does the KPI impact computer?
How does KPI impact?
How is it computed?
Oh, how's it computed? I'm sorry, I don't know. But it's a combination of the cumulative relative probability skill score for a whole bunch of variables that users of Met Office forecasts like to use. It would include things like the root mean square error of 2 meter and 10 meter near surface winds. They probably have a big weight on fog over England. Oh, actually, this is a global one, maybe not so much that. There's probably something with the 500 hectopascal anomaly correlate, what is it? Yeah, the anomaly correlation at 500 hectopascals. So that's like the extent to which the 500 hectopascal height surface, the forecast one, looks like the analyzed one. That's probably a big part of it as well. But yeah, there's probably like 50 different components that go into that. So it's fairly exhaustive. And exhausting to go through all of it. Yes?
So if a modelling centre was only going to produce a new forecast every, say, 2 days.
Yes.
So you only need good initial conditions every 2 days. Would it make sense for them to do this data assimilation cycle every 6 hours or more frequently then? Or would you always try and match when you wanted to set off a new forecast for that cycle?
That's a really good question. Did everybody get that? It's this question about the data assimilation length. So the ECMWF has better forecasts than the UK Met Office. This is number 2 in the globe most recently. And one huge advantage the ECMWF has is that they get 12 hours to form their analysis, whereas everybody else is just only giving themselves 6 hours. And so it's sort of an apples oranges comparison. The playing field's not level when you compare the ECMWF with everybody else. And I think a lot of people think the reason is the 12 hours. I don't think it's that clear. The beautiful thing when you have a long data assimilation window, we'll get to this later, but there's this technique called 4D variational analysis. And what you actually do is simply what's going on is you make a forecast with your nonlinear model, using that prior, and off it goes, and you've got all these observations lined up. Say, of the next 12 hours or the next 6 hours, or it could be, from what you just said, 2 days. It could be 48 hours. What this scheme does is, so there's this forecast that goes along and it misses all these observations. It's just missing them. It's not very close to the observations. And then what it does, it takes a gradient of this measure of how much it missed the observations with respect to every single variable in the model at the initial time. Yeah? So it's this gradient of this distance, how far away from the observations you are. So you know where to go. You know, well, if I change the initial condition this way, if I just move a little bit, it's like you're on a hill, and there's contours, and you want to get to the top of the hill. You know, well, if I go this way, I'll get up the hill, I'll get close to the top of the hill. And so they can find this initial state that actually gives a trajectory that gets you to a local minima in this distance from the observations. And so that's a really powerful thing if you can do that. Because now you've got this model trajectory that's just like following the observations for 2 days. And if it can do that, you've got to get a lot of things right. Yeah, so that's where we are at the moment. Nobody can do that for 2 days. It sort of starts running out of steam at about 12 hours. And it's partly because the models are bad. It's partly because this minimization problem gets very ill-conditioned. There's very, yeah.
So I would have thought mostly that how often that cycle is probably dependent on how often they want to produce.
There's that, yeah. And that's part of this thing. Like if you're forecasting small-scale convection, you want to do it every 15 minutes because somebody like you is deciding when to ride their bike home. Yeah.
So, and what you said though is that there's no advantage, it seems, to doing the cycle more often than you need it for the initial conditions.
Okay, well, so here's another. So there are these competing sides of data assimilation here. There's also theory that says if you could perfectly model the uncertainty in the forecast, in the observations, then doing it every 15 minutes, as far as the forecast is concerned, would give you the same result. Exactly the same result. There would be no difference. Yeah, there's sort of fundamental limitations here associated with information, yeah? So if you can somehow, when each observation comes in, completely absorb that information, it doesn't matter, yeah? So it's this thing about having a data assimilation scheme. Where am I? Yeah, a data assimilation scheme that completely preserves the information from before, yeah? And so these things are like, there's different approaches, and it's like, so when you do 4D var, it sort of forgives you for being bad in the way, like you could do this kind of badly, like specify this forecast error covariance badly, and it would sort of overcome that weakness in one method. But then if you can specify this, the uncertainty in this very well and not lose that information when you do the data assimilation, in principle it wouldn't matter every 10 minutes. So there's sort of competing skies. So there's some people who say, no, we're going to do it every 15 minutes because we can produce more forecasts and there's no theoretical reason why it should be worse. But practically, at the moment, it seems like really having that 12-hour cycle is giving the ECMWF a benefit. Okay. Yeah.
Shouldn't the upgrading time, like 12 hours or 2 days or whatever, be depending on the range of variability of the variable themselves as well? I mean, of the observed variable.
Yeah, beautiful. So this is right on it, yeah. So a lot of these data assimilation techniques assume a quasi-linearity in the dynamics, yeah? And so if you think about a convective cell in the atmosphere, that becomes nonlinear in like 30 minutes, an hour. So that's another reason why people who are assimilating radar information are like doing data assimilation every hour or half hour or 15 minutes because it gets really nonlinear. And, you know, the ECMWF is not resolving convection. They're just ignoring that problem. The radar data is not going in, yeah? Yeah, and that's also why the ocean people can get away with the 10-day data assimilation window because things are evolving really slowly. And so things kind of stay linear for 10 days or even longer. So, yeah, that's an issue as well. But theoretically speaking, you know, you could do it, you know, you can take the gradient with respect to everything and find local minima and stuff like that. So it's, yeah, there's lots of ways of coming at it. Yes?
So, I'm wondering, during 4D var assimilation, you're forecasting to the initial conditions. Well, how does it work?
Okay, well,
Confused.
okay, no, let's try and do it now. I do have slides more on that, but let's try and do it right now. So what's happening with 4D var is you're actually estimating past conditions. So it's like, let's take, so if I was doing 4D var right now to do an analysis, yeah, for the time right now,
You go back in time.
I'd go back in time. I'd go back in time at least 12 hours, yeah, if I was doing the ECMWF. And then starting 12 hours earlier, I'd launch this forecast and I'd see how different it was from all the observations, and then I'd do a minimization procedure to give myself a forecast that is matches the observations pretty well over the last 12 hours. And then, so I've got this forecast that's constrained by observations for 12 hours. And then what I'm going to say is, you know what, I'm going to use that as the initial condition for a forecast into the future. Yeah? Right? Okay. Good. Lots of people do. You're not the only one. Okay. Yeah, so it's actually had... So these improvements I was showing here... Where did I put it?
Just in front of the white project.
I'm very absent-minded. Yeah, so all those improvements actually, I mean, I think a huge thing is like the feedback between like making a model improvement and then improving the model. This stuff actually doesn't show that. That's just from improving the initial conditions. But over time it does. To what extent does data assimilation contribute to climate research? Obviously, you think initial conditions, it's a prediction. It's not a projection, yeah? Because we're using the initial condition information. But what do you need to look at if you're checking out the performance of your seasonal forecasting model, or you want to get an overview of how climate's changing? You want to look at what's been happening over the last 40 years. So the most cited climate paper is actually a data assimilation paper. And what it did was it went back 40 years using a fairly up-to-date data assimilation scheme and made analyses of the state every 6 hours and made that available to everybody. And that's this NCEP-NCAR 40-year reanalysis project. Yesterday, that paper had 27,000 citations. Yeah. Most of us in our careers, if you sum up all our citations, won't manage that.
So this is top 10 in what, all of science or just climate science?
This is climate. So this is from an article in 2015. I mean, I don't know if this is still true. In 2015, that was the top-cited one. And so this is McSweeney, this Carbon Brief. This is actually in the category of climate-related, because obviously, you know, it's just the reanalysis. They didn't say anything. They just said, here's the reanalysis. You know, they didn't make any claims about climate change or anything. All right. Okay, I mentioned this. As data assimilation gets better, better analyses, better exposed model error, leading to better weather and climate models. Data assimilation improvements go hand in glove with model improvements and vice versa. Essential that data assimilation developers work closely with model developers and that they understand each other's challenges. The ECMWF is really good at that. Some centres, they kind of like get into separate groups and blame each other for the mistakes in the forecast. Doesn't help. Makes you feel better, but it doesn't help. Okay, and here's an example of a pretty impressive improvement. So there's a measure of rainfall, the continuous ranked probability skill score, that's what I was trying to say before. See up here, yes, for rainfall, and it's positively oriented, so when that's a big number, you have lots of skill, and when it's a small number, you don't have much skill. And so when it drops below 0.1, you really don't have much skill at all. So this is kind of like the time to complete loss of skill in your forecast. You can see in 2001, after 2¼ days, basically there was no skill in the precipitation forecast. But now, that level of skill you get at 7 days. So, yeah, what in 2001 you could know 2 days ahead, you can know 7 days ahead. So think what impact that makes on agriculture, on managing hydroelectric power, stuff like that, yeah? You've got an extra 5 days to plan, to think what you're going to do. Are you going to put your harvesters out today because later the ground will be too wet to put your, to harvest the wheat? There's a gazillion implications of being able to do that. Okay, this is a climate-related one. So this is actually a guy from the ECMWF, boundary layer expert. But if one could magically cover an additional 4% of the globe with low cloud, so this is, I don't know, so this is like low stratus they're thinking of. I don't know if you've ever been to California or the west coast of South America or the west coast of South Africa. Particularly in the summertime, you get these low clouds. It's often like sea fog. It's just sitting over the ocean. It makes it really cold. You're like close to the equator, but it's really not warm at all. Anyway, they spread out of the ocean. So there's these huge cloud decks of very low cloud, and they're really good reflectors of incoming radiation. They happen everywhere, but they happen to be focused in those areas. But yeah, if you could increase those by an additional 4%, doubling of the potential doubling of CO2 could be offset. But if you look at the climate models, they're all split into those that increase low cloud and those that produce a decrease. It turns out that clouds and precipitation are also a major source of model error in weather prediction as well. If you track forecast busts, so days when the weather forecast error was really big, particularly studies have been done in the Northern Hemisphere, it corresponds to days when there was lots of convection. At the time the analysis was made or just after that. Until recently, observations of clouds and precipitation in the data assimilation schemes have been studiously avoided. So you can read whole bunch of papers on satellite data assimilation, satellites and clouds. And nearly all these papers are about how do I detect the clouds, not so I can assimilate that into my model, but how I can just like not assimilate it. Yeah? So that's what I mean by studiously avoided. So, if you're just ignoring the major source of information that you have about something, you shouldn't be that surprised that your model's really bad with that. And one of the big things that's happening now is we're finally starting to get into assimilating these cloud-affected radiances. And actually, you might have heard about clouds with very high concentrations of supercooled liquid water that turn up over the Southern Ocean. One of the things that's highlighted that is, the data assimilation people were just like looking at the radiances and going, this is not an ice cloud. And all the models have it as ice. And they could tell from the radiative properties of it that it wasn't. And so part of the thing in data assimilation is you kind of need a good model forecast to be able to assimilate it. Yeah, okay. There's another problem with our data assimilation schemes of that, apart from it not being modeled very well, is that most of the current data assimilation schemes we have assume that the error distribution of the forecast is kind of symmetrically distributed. It's Gaussian, multivariate Gaussian, and we assume that for the observation errors, and we assume that for the forecast errors as well. And that's a really bad assumption for something like relative humidity, which is bounded on two sides, or rain, if you wanted to assimilate rain. Your rain has actually, if you think about the probability distribution function for that, normally there's a direct delta function at 0. The probability of 0 is always quite high. And then after that, it's some like skewed distribution, gamma, log normal, something like that. And so when you try and do that with a Gaussian, all sorts of terrible things happen. Okay. This is the main one. So you guys are all going to learn how to do perfect data assimilation right now, better than anything that's being done on the planet. Yeah? And you're going to do it by a thought experiment. Okay? You walked in here as mere mortals, yeah? But for this thought experiment, you have to imagine you are gods with an omniscience that almost in history nobody has attributed this sort of omniscience to them before. Yeah, particularly if you think about the Greek gods. They hardly knew anything. Okay, so imagine that there are an infinite number of Earths just like our Earth. Yeah? So you can imagine that you're going to find these Earths by traveling off through the universe and just finding Earths that are like ours. The continents are in the same position. The oceans are in the same position. The greenhouse gas concentration is the same. Each of these planets are full of humans, a bit like us, but they're sort of random realizations of us. You know every day you make choices that you could have done differently. On these other planets, those people are taking the different choice, yeah? And the butterflies are flying in different directions. So on each of these planets, the realization of the weather is different, yeah? The climate is the same, but the realization of weather is different, yeah? On each of these planets, people are taking observations. They have thermometers that they're putting into the air, yeah? But on each of those planets, so a thermometer is never perfect. It's incurring some random error. And the thing is, on each of these planets, their thermometer incurs a different random error to our thermometers. Yeah? So each of these Earths is getting a different random error. Another thing to think about with data assimilation is, remember, what we're trying to initialize is a model, which are these big grid boxes, yeah, that we have there. They're these averages. So the perfect initial condition for one of these grid boxes is not like a thermometer reading at some point in that grid box. It's actually the average value of the temperature over the entire grid box, yeah? And a thermometer does not measure that. So there's a big error of representation. You'll also remember Todd's talk from Monday, where he talks about the real resolution of a model is actually about 7 by 7 by 7 of those grid boxes, so it's actually a much bigger area than that. Remember how he was talking about effective resolution, and it's not the grid box size. It's not 2 times the grid box size. It's much bigger than that. Okay, so there's an error of representation incurred with all these observations as well. And I want you to realize that that's going to be different on each of the different planets. Yeah, so errors of representation could be like here in Melbourne in the summer, we'll get a sea breeze coming in off the bay and moving over the city. So on all these different planets, there's a different Melbourne. Yeah, on any particular summer day, there'll be a sea breeze moving in, but that will be in a different, it'll move in at a slightly different speed. And so when you take an observation, so you take an observation at the Melbourne Arts Centre, next to the Yarra, and one of the Earths, that'll be cold because the sea breeze had made it past you, and another one of the Earths that'd be warm because the sea breeze hadn't got there yet, that sort of thing. Okay, so imagine all of that. And each of these planets have a satellite like GOES-16. So these are geostationary satellites. They have incredibly high-resolution cameras on them. They're measuring in about 6 different wavelengths, including visible wavelengths. These satellites can give you a half disk of the Earth every 10 minutes. And in some of the channels, it's at 500-meter resolution. So it's just an extraordinary amount of data. So each of these Earths has one of these. And when we look down over our Earth, this is what we see. This incredibly detailed cloud pattern with things happening at a vast range of scales. Yeah, and off it goes. We'll just let it run. What else can I say? But you can see there's large-scale aspects to it. See how everything's sort of moving north? So there's definitely a very important large-scale aspect, but there's all these small-scale things happening as well, all this banding in the clouds. You can see there's clouds at different levels. We've got some convection starting now. This is over the northeastern United States, by the way. You can see clouds. Yeah, so can you see the shadow of the clouds? So that's actually telling you something about how high the cloud is, the cloud top is. Yeah, there we go. So now we continue with our thought experiment. So you are omniscient, yeah, and you get to know what all these different planets, what's being seen by their GOES-16 on all these different planets. And you find an infinity of planets that have exactly that movie loop, as far as you can tell. Yeah? So they all have that movie loop. But because that's just showing the low-level aspects of the system, it doesn't define everything. Yeah? It defines very well that region of the United States we were just looking at. But there's lots of other regions it doesn't define very well. So, for example, on the other side of the globe, off Australia, let's say 10 kilometres away from King Island in Bass Strait, we have another type of observation. So another satellite observation that's pretty interesting is SSMIS. And what it measures is kind of very small undulations in the surface of the ocean that are related to the wind speed or the low-level wind kinetic energy. So you have an observation of wind that has no directional information. It's just how strong the wind is. Yeah? And we could imagine that in all these Earths that had the same movie loop from GOES-16, they have the distribution of, so just with this diagram here, I'm putting these red crosses for each of the replicate Earths. And you can see that there's sort of a concentration of them around here, and there's a few out here, and there's a few out here. So down here, this is, let's just suppose that the instrument is measuring u squared. So we're going to have an observation of u squared. But so each replicate Earth has a value of u. Yeah, the abscissor axis here, the x-axis is just u. And the ordinate axis, the y-axis, is u squared. You can see there's a concentration here of around, I don't know, 0.5 or whatever. So that's what's happening on all the replicate Earths, and you, as omniscient beings, know that. And then, there's a random error that occurs on each of these planets, yeah? So these crosses are the observed values of u squared. So each observed value is the actual value of u squared plus some random error. And you can see how in this diagram the errors seem to be bigger when the wind is a larger distance from zero. See how you're getting like really big errors over here, stuff like that. But round here there's hardly any zero. The reason I did it like that is you can show that if you have a unbiased observation of a bounded variable, so by unbiased I mean if the truth is here, so suppose that's zero and the truth is here, and my observation error is just a random process around that truth. So when I say it's unbiased, that means the average of all those random errors will be zero. And you can imagine when you have a bounded variable, you know, the error is bounded on this. Say if that's the zero and this is a bit bigger than zero, the error can't on this side can't be bigger than that. Yeah. So if the errors of the opposite sign are going to balance that, they can't be that big either. So it actually goes to zero as the truth goes to zero. So we see not exactly this behavior, but behavior like that in actual instruments. Okay, so that's what's going on there. And then what we find in our Earth is an observation of that value. And then you, as omniscient beings, can say, well, all these mortals living on these planets don't know what I do. What can they know? They can know that what the observed value they had was 1.16. And so maybe there'd be some way, like if they knew what I knew, which is all these replicate Earths, where they could group together all these replicate Earths that just happen to have an observed value of 1.16. Yeah? And so you can see how you could have a true value of u down here at 0.5. And so that gave you a u squared value here of the square of 0.5. 0.25. But that can actually have an observation that's equal to 1.16. Yeah? And there's values over here that can have, where you can have a true value. The true value can be here. So the true u squared value is up there. But you can have an observation error so that the value actually observed is 1.16. And of course, this can happen for negative values of u as well, because, you know, the square of a negative number is a positive number. And so you actually, if I plotted the density of the replicate Earths that gave an observed value of 1.16, I'd see two humps. I'd see a hump here, and I'd see a hump there. Yeah? Is that clear? So that's ideal data assimilation. That's what we're trying to do. That's just it. So it's that thought experiment. Sorry? Okay, yeah, sorry. So just to flesh that out, I'm trying to add additional information. So the prior density, so in this case, you know, I said I want all the replicate Earths that had the same movie loop of that GO 16, yeah, in the Northern Hemisphere. But then off King Island, there's a density of u values. Yeah, and so this is that solid curve down there. That's the prior, before I do data assimilation, of this observation of kinetic energy. That's the density. Yeah?
From using all the u values.
Yeah, so that shape there, that Gaussian shape there, is actually giving me the density of these crosses. Yeah? In the u direction. And then, okay, what do you think this one's about? What do you think that curve there is about? The solid line there. What do you think that one's about? Yeah, you've got to put your head on the side. So that's actually the same thing, but it's for u squared. So if I go back to here, you know, you can put your head on the side and ask, well, how many of these red crosses have a u squared value equal to, say, 1? Yeah? How many of these have a u squared value equal to 0? Yeah? Etc. And if you look at that, what you see is actually the most likely value of u in this situation is 0. So it goes right up here. Yeah? Look how non-Gaussian that distribution is, yeah? It's completely asymmetric. A Gaussian would be a horrible, horrible assumption for that. But that's what we're doing at the moment. We're assimilating these obs, and we're just pretending, oh, you're Gaussian. And then assimilating it. It doesn't work that well. But then this true posterior distribution, like once we've taken this observation where we had an observation of 1.16, then that posterior distribution, so now this is the distribution, can you see all the crosses that are on the parabola there? That's that density there. So that's the posterior distribution there. Yeah? So it turns out that these two distributions are well modeled by gamma PDS. Yeah? Log normal would be horrible for this one. You'll recall that log normal always assigns zero density to 0. Gamma's not like that. It can assign finite density to 0.
Right, you said this is data assimilation, but is this like ensemble kind of filter type data assimilation?
This is what nobody is doing anything like this. You have just done in your heads data assimilation that is far beyond the dreams of mortal data assimilators at the moment. But that's what we'd like to do. That's what we're trying to do.
So it's giving an ensemble of possible initial conditions rather than a single one.
Yeah, absolutely. This is what state estimation should be about. You know, in science, yeah, one value is rubbish. You must give the uncertainty of the value. Yeah? You must maintain uncertainty. Yeah, so estimation theory is very strict on that, and it just, if you mess up with that, the whole thing falls apart. Yeah. Okay, so the next thing, Matt just asked about, is this kind of an ensemble method? It is an ensemble method. You could imagine if you could just generate an enormous ensemble, you could do exactly what I did here. You know, you could just try and find members, I could generate random observations for each of my ensemble members, just like I did here, and then just like pluck off all the ones that happen to be close to the obs. Particle filters basically do that. Yeah? So if you have a low-dimensional system with about 10 variables, there's this data assimilation scheme called the particle filter, and that's what that does. But okay, actually, that's a great question. Leads in. So imagine, so you can see here, my posterior distribution has 2 humps in it, yeah? So you guys might have computed like histograms before. Like, you know, you've got a big sample and then you compute the histogram. And you know that, like, when you do a histogram, if you don't have many samples, it's a really noisy histogram. It sort of just looks like rubbish. But as you increase the sample size, it starts to get smooth. So how many members, you know, if you're doing histograms, do you think you'd need to sort of get a smoothish, like, 2-hump feature like that? Any suggestions? 1,000, yeah. So there you go. So to get bimodality in one direction, we need 1,000 members. Yeah? Okay, so now let's imagine we've got a 2-variable model. Yeah, so here I just did U. Yeah, so the zonal component, we could do V as well. Yeah, and that might be bimodal, but in a different way to this. So we'd need 1,000 times 1,000 members. Yeah. So we already need 1 million members, and we've only got 2 variables. Yeah. So it's like 10 to the 3 to the power of the number of variables in the model. So that's 10 to the 3 to the power. The power is 10 to the 6, yeah? And that's probably a bigger number than the number of protons in the sun. I don't know. But, you know, it's sort of astronomical values.
Why would we need more members?
Right?
If we want to sample more variables, why would we need more members? One member doesn't have all the variables.
Yeah, the members, so here we're just, let's focus just on one variable here. So this is just one variable at one grid point, U. Yeah? You agree that takes, I need 1,000 members to represent a double hump distribution there, yeah? You agree with that? So now suppose we've got another variable. So we're just looking at V, and that goes off in this direction, but it's got a different double humped distribution, yeah? But I've got to describe this over a plane. I now have a 2-dimensional plane. Yeah, so there's U in this direction, V in this direction. and I'm going to have this like density plot, this contour plot of the densities. And so all I'm saying is to fill that up on the two-dimensional plane so that you have a smooth histogram with like, well-defined maxima and minima on it. I need 1 million members. 10 to the 3. Yeah, 1,000 times 1,000. Yeah? Okay. How am I doing for time?
11:36.
Another 20 minutes?
20 minutes? All right, okay. All right. So there's the next thing I wanted to say. This is a workshop, so you need to do some work. So I'm going to so get out your pens. We are about to derive Bayes' theorem. Some of you may know this theorem already, but if I'm going to relate it to the question we had here. So I'm going to start by, and I want you to start with this as well. Let's just try and draw this picture in your notebooks. Okay, roughly. We'll sort of be switching back and forth between this one and this one. So let's go. Okay, I guess I'll draw this side. Will that work? So you come to the front if you need to. Okay, so I'm going to try and draw that picture. So here we've got, it's the y-axis. So this is y equals u squared plus some observation error that I'm calling epsilon 0. See that? And then this side, we've got just u, and we're going from it's minus 2, it's like plus 2, it's 0, so it's like minus 1, minus 2, 0, 1, 2, 3. And then here we're going 5, 10, 15. And then we've got all these realizations of truth, which is kind of this red line. Let's see, we're going to go up to about 10. There, something like that. And then here it's going to like peter out around 2. Got that a bit high. And then we've got observations around that. Yeah, so when as you draw these dots on the page, think of the stochastic process. Yeah, so here so there's a replicate Earth. Yeah, there's an Earth where the u value was equal to 2.5, and the true u squared value was just the square of 2.5. Yeah, and then on that Earth, there's an observation of u squared, and a random error is incurred, so the observation, say, ends up being there. Yeah? But on this Earth over here, I get a different signed observation error, and it ends up there. And here it's a different one. Yeah? So we just kind of, you can just draw yourself random dots, a bit like I've got on the page there. So stuff like that. All right? So each of those black dots, yeah, which is just 2 values. Each of those black dots, we've got, so one of those black dots, I'll just point at that one there. It's got a u value and a y value. Yeah, it's just 2 numbers. So y is the observation and u is the true value. Yeah? That's it. So I could ask, what's the probability? Where's a good spot? I don't like my black dots. All right, so I'm going to just take a particular value, a particular range of x here. So let's consider true values of u between this value, about 2.1, and this value, about 2.5. And then also let's consider a range of y values. I'll try and draw a horizontal line here. And say this value down here. And I don't happen to, I might just fill out a few more black dots there. That's all right, I guess. If we just... Okay, so I could then ask, so how do we do, what are probabilities about? It's always just about counting, yeah? Probability is always about fractions. Fractions of stochastic processes. So here, this is, I haven't drawn, of course we had 1 million replicate Earths and I've just drawn a little subsample of that. But, within this little subsample, I could count up the number of all the black dots on this picture, yeah? So that's like the total number. And then I have this little fraction here, and this is the fraction, so everything in this box, I want you to focus on that, yeah? And we can think about what's the probability. So what I'm going to do, I'm going to call this, I hope you don't mind, I'm going to call it, like when u has this value between these two values, I'm going to call that x. Yeah? Big X, capital X, I'm trying to draw there. And when it has a value between these two values, I'm going to call it capital Y. Yeah? So the probability that, there's the probability of there being black dots in this little box here, that's the probability of X and Y happening at the same time. Yeah, so that's within that box, that's a P for probability, X intersecting with Y. So the probability of X and Y. Yeah? That's what that is. And that, if we just did it physically, we'd just count the number of black dots in that black box and divide that by the total number of black dots. Black dots. That's all that is. Yeah? And then there's two different ways we can represent that. Other ways we can represent that intersection. So one way we could do it, we could say, okay, there's this, I can define a probability of there just being y. So the probability of there just being y, let's go, draw it here. So just to be explicit, the probability of there just being y, that's the number of black dots between these two blue lines divided by the total number of black dots. Yeah? That's all the probability of y is. But then I can also say there's a fraction of the dots in here that have an x value have a u value that falls in that range given by x there. Yeah? So that's, if I multiply this by that fraction, and there's a name for that fraction, it's the probability of x given y. Yeah? And that will give me the same fraction as doing that. So they're equal to each other. Does that make sense? But of course, I can do it the other way as well, yeah? So here I focused on this. I just did probability of y, and then I took the fraction within, those two blue lines. But I can also look at it this way, up here. Yeah, and I can say, well, there's a probability of that x value there happening. And then I can ask, what fraction of all these points in here actually have that value of y? And so that's the probability of y given x. Yeah? So they're equal to each other. So what's kind of going on with data is, well, what is going on with data assimilation is we run an ensemble forecast, we look at historical data, and we figure out what this thing is for different values of x. So I've just shown you on this diagram the value of this when x is this value. But you can imagine I could do this with other values of x as well. We could repeat this procedure with other values of x. So that's something I can figure out. I can figure out what this is. Or I can estimate it, guesstimate it somehow. And then the other thing is, so this is the, remember that y is the observed value. And so this is saying, what's the range of observed values you could have, like if you knew the truth? Yeah, and that's something I can get partly from the manufacturer of the instrument. The manufacturer of the instrument might have a really accurate one that's too expensive for you to buy, but then he's got one that's not so accurate that you can buy. And you can compare those two to tell what the range, for a given true value that you measure with a very accurate instrument, what's the range of observed values from the less accurate instrument. And then you can also do games with the error of representation if you know something about the subgrid scale flow. So we can know that and that. What we'd really like to know is this thing here. We'd like to know, given this prior information, this P of x, which is basically this initial, so if I go back, so we had, see the, on the bottom curve there, we've got the Gaussian, that's our prior information. So given, we knew something about u, yeah? U was constrained between -2 and 3. We knew something about about u. There was prior information there. So we have that. Just there. We have that information, and we have this information. But what we want to know is this distribution of x given y, and that is this thing in the bottom here, this double hump thing, yeah? So for each value of u here, we're getting the probability of the truth, u being equal to that value, given the observation. So we can get that just by rearranging this equation. So, this equals that. So that means that P of the truth given y equals the prior probability of x times, we call this second thing the likelihood, the probability of y given x divided by the probability of y. Yeah? So this is Bayes' theorem. And this is what data assimilators are trying to implement, one way or another. Yeah, but that's the basis of it all. How much more time do I have? 5 minutes. Okay. I won't have time to go through everything else I was going to go through, but that's fine. So that's Bayes' theorem, and if we could do that, the problem would be solved. We can't do that. We don't have the computational resources to do that. And so we make approximations. The data assimilation, much like numerical modeling, it's like parameterization scheme. It is you're trying to make artful approximations. Approximations that are computationally affordable but get you close to solving Bayes' theorem. Bayes' theorem, yeah. So one approach is to just say, and this is what's done at the Bureau of Meteorology in the Met Office at the moment. So it has different forms. 40var, if you don't do an outer loop, has this form. The ensemble Kalman filter, I don't know if you guys have heard about that, but that kind of does the same thing. The Deutsche Wetterdienst does that for its convective scale forecasting. And basically, it's a really simple idea. All they're just saying is, well, I reckon the truth is it's the mean of my ensemble forecast. I'm going to do an ensemble forecast. It's the mean of my ensemble forecast plus a matrix times this V thing, where V, each row of the vector V is some function of an observation that is thought to be a useful predictor of the forecast error. Typically, V will just be, that vector will be the difference between the list of observed values and the mean of my ensemble forecast of those observed values. Of course, if you have an observation, you can make a forecast of what that observed value will be. And so data assimilation is driven pretty much by these differences between the observed value and what forecast you made of that observed value. And anyway, you can say, well, if that was true, then one property I'd want for this, this K is that I'd want to choose a K so that it made this sort of random component, which we call the analysis error. I wouldn't want this thing to be correlated with this difference between the observation and the mean of the ensemble forecast. Because if it was, it means I could find a better K. So anyway, you can do that and do the math, and you get the ensemble Kalman filter or 40var with no outer loop. But for the problem I just showed you, I just want to show you how terrible that is. When you have this non-Gaussianity, it's also nonlinear, yeah? U squared is nonlinear. It's very simple, but it's very nonlinear, particularly when the mean of the distribution is close to 0. And so if I did that to compute this true posterior and I did the density, I'd get this function here. Yeah, the mean of it's not too bad, but it doesn't get the idea that it's bimodal. Yeah, so not very good. There's this 40var thing that we spoke about before that Boris liked. and so it has it actually has this nonlinear outer loop that ensures that any analysis of U you make is completely consistent with the U squared analysis. So the ensemble Kalman filter doesn't do that. The ensemble Kalman filter, or this best linear unbiased estimation, it happily analyzes a U squared value that is not equal to the square of the analyzed U value. So you have these like physical inconsistencies that turn up because it's a nonlinear relationship, but this thing's just assuming linear relationships. So 40var is nice in that all the analyses turn up on the parabola where they should be. It gets a little bit of the bimodality, but you know it's wrong, and it's wrong because it's making a whole bunch of Gaussian assumptions. It's time for me to end. I was just going to show you, if there was time, I don't know how long I'd spend on that first bit, but I did want to spend most of the time on that first bit. There was other stuff to talk about, DAs related to ensemble forecasting, statistical modeling, observational network design, model tuning. And I won't really talk about the other stuff, but this is stuff associated with directing planes, where to take observations to improve forecasts. And we had a program going on this through the 2000s at NCEP, and when we first started it, it really gave a lot of improvement, about equivalent to 20 years of advances in numerical modeling and data acquisition. But the satellite data set, we're not quite sure why, but anyway, this improvement went away after 2011, which I guess proves that wrong, actually. It was only 10 years. Because we got a lot better at assimilating satellite data, and the value of these extra observations went down. I won't talk about that. There's my summary. We've kind of run out of time, and you can read that. It's pretty much everything I've just said. Thank you.